Greetings, this is Greg. Let's talk about the Junkers Jumo 004 turbojet engine as used in the Messerschmitt 262. We'll talk a little about the history of the engine, then explain how it works and how it relates to modern turbojet engines. This video is a remake of the very first video I put up on this channel. I've remade it primarily to fix some audio issues that were caused by Microsoft Movie Maker, which I stopped using after about the third or fourth video on this channel. The Jumo 004 was one of the most historically significant engines of all time. It was the first jet engine to see operation in combat, and the only one to do so in significant numbers during the Second World War. Furthermore, it was the first jet engine with the now common axial flow compressor design. We'll talk about what that means in technical terms later, but in practical terms it means that this engine paved the way for most civil and military jet engines which followed. Let's take a look at the ME-262. It features two of these engines, one under each wing. They draw in air at the front and expel exhaust out the back. The 004 is a true jet engine. It is not a turbine engine that's powering a fan, propeller, or anything else. It is a jet engine which propels the airplane forward exclusively by means of exhaust thrust. Here's how it works. Air enters the inlet at the front of the engine shown here. From there it goes into the compressor section. In this picture, you can see where that's located in the engine. Now let's take a closer look. The compressor section is essentially a series of spinning fans that force air into a confined space, thus compressing it. The first set of compressor blades is called the first stage compressor. After the air passes the first stage compressor, it's forced through stator vanes. These stators serve to straighten out the airflow, and they also give something for each air compressor to compress against. Without them, the air would tend to spiral in the direction of compressor rotation, and thus wouldn't contact the next compressor at the optimal angle. From there, the air goes to the second stage of compressor blades, where it's compressed even more, and then through the next set of stators, the next set of compressor blades, and so on. The Jumo 004 has 8 stages of compressors. All of these compressors are mounted on the same shaft, thus spin at the same speed. The compressors are axial flow, meaning that the airflow is essentially parallel to the shaft. After the air exits the last compressor stage, it enters the combustion chambers. There are 6 of them on this engine. They're called can-type combustion chambers. They are roughly the size and shape of an oxygen bottle. They're arranged radially around the shaft. Since this 004 is a cutaway, it's a little tough to see just how they're arranged. So let's look at another engine for a few moments and then come back to the 004. If you look at pictures of older turbojet engines, you can usually see the can-type combustion chambers. Let's look at the turbojet engine used in the F-86 Sabre. This is the GE J-47. In this picture, the can-type combustion chambers are easily visible. The J-47 came out in 1947, and it's worth pointing out that it looks a lot like a scaled-up Jumo 004. I'm not saying it's a copy, but rather that its basic design looks like a big 004, because in terms of basic layout, Junkers got it right. This is a good time to mention that during the time period of early jets, the combustor cans were simply called combustors in period documentation, as seen in this NACA report. Now, modern turbojet engines don't use the can-type combustors anymore, at least not as far as I know. They've gone to the annular combustion chamber, which is a single ring-like chamber that surrounds the shaft. However, in the 1940s, machining and metallurgy made production of such an engine more difficult, and annular combustion chambers didn't become common until much later. Somewhat ironically, there was one early turbojet with an annular combustion chamber. It was the 004's main competitor, the BMW 003, as seen here. Let's zoom in on that chamber, and you can see it's a continuous ring that goes around the shaft instead of individual cans. I'll come back to this engine later. The designer of the Jumo has been very clear in his writings, as seen here, that with the 004, he was not trying to push the envelope too much, and was trying to keep the project realistic. I suspect that sort of thinking is what led him to use the combustor can layout rather than the annular configuration in use by BMW, but that's obviously just me speculating. He doesn't spell it out like that. There is one other combustion chamber design out there that I think you should know about. It's called cannular, and it's a hybrid of the two, and historically it's been very common, especially in the 60s. It uses individual combustors contained within an annular-like casing. These combustors are connected via holes or tubes so that each can doesn't need its own ignition source. In other words, it doesn't need its own glow plug or igniter, because the combustion fire can spread from one can to the next via the connections. The next type of jet engine was very common until recently, like I say, especially in the 60s and 70s. The Pratt & Whitney JT8D, seen here, uses this configuration. This picture is from Wikipedia, and it's labeled as a DC-9 operated by DHL. That actually kind of annoys me a bit. The plane in this picture was operated by ABX Air. It seems that the ACMI confusion has inflicted itself upon more people than I thought. It's very widespread, and it's even afflicted the editors of Wikipedia. I have an entire video about ACMI, so enough about that. Let's get back to the 004. Now that we have air in the combustion chambers in our example, we only need to add in fuel and, of course, a source of ignition to start the burn. Fuel is added via injectors, simple enough. It's sprayed in continuously in varying amounts depending on the conditions and desired thrust. During engine start, the fuel is ignited by an electrical glow plug. Sometimes on more modern engines, it's ignited by something called an igniter, which is really just a super powerful spark plug. Obviously, you have to have something to start the fire in the first place, so that's going to be a glow plug or an igniter. However, once the fire is started, no further electrical ignition is needed, since any fuel injected into the chamber will be ignited by the fire that's already in there. It's sort of like throwing gasoline onto it is literally throwing gasoline onto an already burning fire. It's just going to burn. In other words, unlike a piston engine, the fuel in the combustion chamber is burning continuously when the engine is running. Thus, normally the glow plugs or igniters are not even on while the engine's running. They're only needed for starting. Now, you may occasionally hear the term flame out in relation to jet engines or other gas turbines. This means that something extinguished the fire in there, and it takes a lot of something to do that. Either an interruption of airflow, a serious interruption, an interruption of fuel flow, of course we'll do it right now, or ingestion of a lot of water, ice, or something else. When that happens, the flame goes out. The engine's still spinning, so you need to reintroduce fuel, air if possible, and a source of ignition. It's a relight procedure, and most pilots are trained to do that very quickly, although most modern engines, and including every single turbine engine I've ever operated, jet or turboprop, can be configured to relight automatically in the event of a flame out, so it's not really a big deal. Now, once the fuel burns, it of course generates exhaust. That exhaust has to go somewhere. It exits out the back of the burner cans at very high speed. As it does so, it encounters the turbine and forces it to spin. The turbine consists of a wheel and blades, and it's mounted on the same shaft as those axial compressors we saw earlier. So it spins the compressors and keeps the engine running. Notice in this picture, one turbine blade is actually missing from the turbine wheel. It may have been removed for testing, or it may have been set up that way for training purposes, I don't know. But on a proper running 004, it absolutely would be there. After exiting the turbine, the exhaust passes through an adjustable outlet nozzle and exits the engine, providing forward thrust. Since this is a pure jet engine, as far as propulsion goes, that's all you have. Of course, there are auxiliary devices and features. There's a starter, for example. This engine has an interesting starter. It's a horizontally opposed two-cylinder engine, sort of like an older BMW motorcycle. Puts out about 10 horsepower. It takes it about 1 minute to get the 004 spinning fast enough so you can introduce fuel and ignition and start the thing. Interestingly, it features the little two-cylinder starter, that is, features a pull start handle. It's a D-ring mounted at the center of the air inlet. You can start the starter by pulling this handle, much like starting a lawnmower, and then use that to spin up the engine. At the rear of the engine, there is a mechanism to vary the size of the exhaust nozzle. It uses a jack screw and a rack and pinion type system, and by moving that onion-shaped thing back there, and they actually called it that, well, they use the German word for onion, whatever that is. But anyway, by moving that thing back and forth, you vary the size of the exit area, and the engine does that automatically for various operating conditions, although there is a manual mode which you would use for start and in some other cases. Now, even today, this is a fairly advanced feature and typically seen only on ultra high performance aircraft, typically jet fighters. That's about all we're going to cover for the mechanical sections of this engine. Most modern jet engines are nearly identical in design and principle. The most significant variation is that most of them now incorporate a second or third turbine to extract more energy out of the exhaust, and then they use that energy to spin a large ducted fan at the front of the motor. So while these are still jets, their thrust comes mostly from a fan and not exclusively from exhaust. As an example, you can see the fan on this A-10's engine. Most modern jets are set up this same way. Much of the fan air bypasses the engine core and flows around the outside of the engine. The amount of air that goes around the engine core versus what goes through the engine core is called a bypass ratio. And most of these modern jet engines out there on airliners and typical airplanes are fairly high bypass. Now at the back of the engine, you can see the area where the air passed around the engine itself and exits out the back. The actual engine exhaust exits out the center of the fan exhaust. And by looking at the relative area there, you can get some idea of the bypass ratio, and this is indeed a fairly high bypass engine. Here's a quick summary of how the engine works so you can keep up so far. We have 4 phases of operation, and in a sense, they're much like a piston engine. There's intake, compression, combustion, and exhaust. Jet pilots often call this suck, squeeze, bang, blow. Let's talk about some of the pros and cons of the Jumo 004 versus piston engine propeller-driven planes like the 109 shown here. The biggest advantage is in thrust. A typical piston engine of the time had 12 cylinders, and each cylinder only creates power on every 4th stroke. The combustion chambers in a turbine engine create power continuously. The combustion never stops as long as the engine is running. Furthermore, the turbine engine can make more and more thrust by spinning faster and faster. This is relatively easy because all the parts are spinning in the same direction and you don't have to worry about propeller tip speed. In a piston engine, you have a lot of parts moving in every possible direction and even reversing directions as the piston engine's crankshaft rotates. This, combined with the limitations of the propeller's tip speeds, make running a piston engine in an aircraft at super high RPM very problematic. Jet engines have the additional advantage of having relatively constant thrust as speed increases. Thus, a jet with, say, 2,000 pounds of thrust will have that amount with only slight variation throughout the aircraft's speed range. The static thrust line on this chart from Aerodynamics for Naval Aviators shows this. Notice that thrust is relatively constant with speed, but that power climbs with speed for a given amount of thrust. See, again, jet engines are rated in thrust, but they do generate power, but the amount of power is related to a combination of thrust and speed. And this means that as your jet airplane goes faster and faster, it develops more and more power, as you can see on this chart. The reason this matters is because an aircraft's maximum climb rate is determined between the difference between power required and power available. This means that a jet can climb at speeds unheard of for a prop plane. I cover this extensively in my ME-262 versus P-80 video, which I'll link in the description. I'm not going to take the time to go over all that again here. The flip side of this, though, is that a propeller airplane with some fixed amount of horsepower, let's say it's 2,000 horsepower, will lose thrust as speed increases. And drag will be going up as speed increases. So this acts as a double whammy to limit the top speed of propeller airplanes. Here's a math formula if you want to play with this. Again, my 262 versus P80 video will walk you through it from the jet airplane side of things. I believe Adam the Engine Nerd has a video that walks you through this really well from the propeller airplane side of things. In addition to power, we have some other big advantages for the turbojet. Surprisingly, it was much easier and less expensive to build than piston engines of the day. For example, Germany's Focke-Wulf 190D9 had an engine that cost almost 3 times more than the Jumo 004, and it took almost 3 times as many man-hours to build. Think about that for a moment. About 1/3 the cost, 1/3 the effort in man-hours, and a lot more performance. The 004's arrival really did signal the death of the piston engine in fighter aircraft. It was much the same over at BMW. The 003 engine was about 1/3 the cost in expense and man-hours as the Dora 9's engine. Now the Junkers 213 piston engine was an awesome engine, but it just can't compare to the 004 in terms of performance. Another issue was fuel quality. One of the primary limiting factors in a piston engine is the fuel's ability to resist knock. This was especially an issue in Germany during the war. However, this simply is not a factor for a turbine engine. They can run on relatively low-grade fuels with ridiculously low octane because knock simply isn't going to happen in these engines. The ability to run low-grade, low-octane fuel was a big plus for the jets. Of course, there were some downsides to the Jumo 004. The most significant issue was probably engine life. Turbine engines run at incredibly high temperatures, especially the aft of the combustion section where the turbine is. In the later stages of the war, the metals needed to resist the high temperatures were in short supply. Germany simply had to do without them. Thus, the production 004s had relatively low quality metals in its construction. Now, to combat this issue, the designers did some pretty clever stuff. The 004 used bleed air off the fourth stage compressor to blow on and thus cool the turbine and some other heat-sensitive components. The turbine is the part that's most likely to fail from heat, so blowing air on that was a pretty good idea. Additionally, in the case of the 004, they could move that exhaust cone to the least restrictive spot to keep temperatures lower during start, because during start, airflow through the core is what's keeping the engine cool, and startup is one of the highest temperature operations for a turbine engine. It's a big part of what shortens the life of these engines. There were, of course, development problems, mostly relating to material shortages. Junkers ran into a problem with vibration-induced failures, actually. Interestingly, Junkers hired a musician to help them correct that. I first heard this story from Bismarck, aka Chris, on Military History Visualized, but the story is absolutely true, and my source for this is from this chapter of this book, which is written by this man who was the designer of the 004, so I'm absolutely convinced it's true. Actually, that book is the source for a lot of the material in this video, and as usual, it's from a very official source. It's from the Smithsonian. The 004's biggest problem was that the relatively high temperatures limited engine life to between 15 and 25 hours. The design goal was 50 hours. It appears that that really didn't happen. Maybe if you had a pilot that was really careful, really getting the engine to maximum RPM on start before you introduce fuel, that sort of thing, moving the thrust levers very slowly. In any case, 15 to 25 hours, not much time, but we need to put that into perspective. The life expectancy of a German fighter plane by 1945 was incredibly short. I don't have any actual statistics on it specifically, but I doubt that planes lasted much more than 15 flight hours anyway. Plus, an engine that needs an overhaul after 15 hours wasn't that bad by the standards of the time. For example, in 1947, so 2 years later, the American General Electric J47 we mentioned earlier had a time between overhauls of 15 hours. Now, that time went way up as the engine was more and more refined, but initially it was 15 hours. It's also worth pointing out, as I did just a moment ago, that with careful technique, a skilled pilot could avoid the temperature spikes and just about double the 004's engine life. So I do think that 50 hours was reasonable, but not realistic, I guess would be a way I'd put it. Those piloting techniques, the details of all that, it's a little bit beyond the scope of this video. I might cover that another time if we talk about jet engine and turbine engine operation. So how successful was the 004? Well, I think it's very successful. It powered not only the Me-262, but the Arado 234 bomber and the Horton 229 flying wing. The 262s shot down over 500 Allied aircraft, giving it a kill ratio of better than 5 to 1, and significantly it did that while being greatly outnumbered. And its basic design lives on in many contemporary engines. With axial compressors, a variable geometry exhaust nozzle, the Jumo 004 led the way for jet engines. Then there's the 004E, E as in echo. This model even had an afterburner, giving it 2,200 pounds of thrust, which is about an extra 10%, a little bit more. This was the first afterburning jet engine, although I don't think it ever made it into an operational 262. BMW 003 wasn't as successful, at least partially because it was never attached to the right airplane. It was used on a Heinkel 162, which was designed to be a lower cost, high production number airplane. In my view, this concept in regards to the Luftwaffe in World War II, okay, not just flat out, but in regards to the Luftwaffe in World War II, this concept was fatally flawed. Even if they could have built thousands of these things starting in late 1944, by that time they had so few pilots that it made far more sense to put those pilots into the superior Me-262. The BMW 003 was also used on the Ju-287. I find it ironic that Junkers put a competing engine on their own airplane. This might have been the dumbest plane of World War II, a 4-engine jet bomber with fixed landing gear. Yeah, you're not imagining that in the picture. That's what that is. I sort of wonder if Junkers didn't bother with retractable gear because they knew it wasn't going to run their own engine, so they didn't really care about its performance, or maybe they knew the war was coming to an end anyway, or maybe they just planned to get to it. I don't know. In any case, 4-engine fixed-gear bomber, that's just not gonna work in 1945, let alone 1946. All this weirdness aside, there's no question that these two German jet engines were far ahead of their time and paved the way for what was to come. Have a great day, and goodbye for now.